Hello everybody, and welcome back as we continue on the journey that is the 2011 CSMC. That's the Canadian Senior Mathematics Contest paper. It's for the upper level sort of high school age mathematicians. We're on to question number 6, which is the final question in part A. Part A is the just need a final answer. It's not as worth as many marks, I believe. I can just double check. Yeah, each question here is only worth 5 marks, so it's nothing really to stress about. So we're almost done part A. We're going to get into part B in the next video. So if that's what you're looking for, you're going to have to go to the next video. But yeah, let's finish off part A, and then we can get to part B, where the marks are higher, but the solutions are more scrutinized. Okay, question number 6. In a magic square, the numbers in each row, the numbers in each column, and the numbers in each diagonal have the same sum. Given the magic square shown with A, B, C, X, Y, Z all positive, determine the product X, Y, Z in terms of A, B, and C. All right. My word. Okay. So, we want the product X, Y, and Z. We know A, B, C, X, Y, and Z are positive. We know nothing about these P, Qs, and Rs. But it's a magic square, so the sum of the columns, the sum of the rows, and the sum of the two diagonals are all going to be the same. Now, it probably looks very scary, I won't lie. Most questions that have logs or functions that they just make up and don't properly describe, they always look scary. They look like they're the scariest questions around, but they're really not. You just have to treat log A as though it were a number. And sometimes the properties of log might come into it. Like I noticed that we're going to be looking for a product X, Y, and Z. Okay. But if we've got a product X, Y, and Z, but we're adding up, like the constant value is log A plus log B plus log X. The properties of logarithms allow us to turn that sum into a product, and maybe that's where we're going to get our answer here. So let's go to the scrap paper, and we're going to copy down our magic square. We have log A, we have log B, I think P was down here. We have log X, I think there was a Q here, and an R, I think this was log C, and I'm pretty sure this was log Y, and this was log Z. Okay, let's just double check that before we move on. I just hate bouncing back and forth, that's why I'm going to copy our magic square into our scrap notebook that we've been doing our work on. So yeah, X, Y, Z along the diagonal, P, Q, R, A, B, C. Everything looks good. Okay. Now we're not given any actual values, so likely we're not going to be able to solve for anything. We could probably solve for P, Q, and R in terms of the X's, the Y's, the Z's, the A's, the B's, the C's, but I suspect that they're just there to confuse us. So, instead of trying to maybe figure out the magic constant, what I could probably do is compare rows and columns and diagonals that intersect. So I'll show you what I mean. So the top row added up is the same as this antidiagonal, which is log Z plus log Y plus log X. Now you notice they both have a log X in here. So we can actually cancel that out. Right? Cancel these two log X's out. And you're left with log A plus log B is log Y plus log Z. Okay. But logarithms, if you add up two logarithms with the same base, and all of these do have the same base, a base of 10, incidentally, adding up logarithms of the same base is the same as multiplying the two numbers inside the logs. So a times b, so log a times b is the same as log y times z. And if we raised both of these to the power of 10, or we just knew some other properties of logarithm, we could easily see that AB is going to be the same as YZ. Okay, so now we have YZ, and that's a part of the product we want. We want a Y times X times Y times Z, and we want that in terms of A, B, and C. But we have Y times Z in terms of A, B. And all we did was we looked at this row and this column. Okay. Now, these PQs and Rs make it really hard to just do something similar and compare only logs to the other logs, so ABCs and XYs and Zs. For example, we wouldn't want to do this column added up with this row because we'd have this Q in here that we just couldn't handle. Sure, the R would cancel out, and we'd be left with log Z plus Q is the same as log X plus log C. But we don't have any way to really understand what Q is, which is a shame. But there are a couple places I'm noticing where, we're going to have a PQ or an R in there, but it's going to be the one square in common. So, for example, log A plus P plus log Z is going to be the same as P plus log Y plus log C. Well, the P's on either side of that equation are going to cancel out. Right? We've chosen to add up this column and this row specifically because they both intersect at P. And so P will be common to both sums, and we can ignore it. And we can work out that AZ is equal to CY. Just writing everything alphabetically. Okay. Well, add AB equals YZ, and we have AZ equals CY. So we're starting to get more information about the relationships between A, B, C, and X, Y, and Z. So here we had all logs, and that worked out fine. Here we had a common value of P. Can we get a common value of Q in this? So this column and this row intersect only at Q, but we're going to be left over with an R. Okay. What if R was the common term? So this row, this column, they both have R, but this one has a Q in here. That's not going to be helpful. But this diagonal and this column, they both intersect at R, and everywhere else are logarithms. So log A, log Y plus R is the same as log X, log C, and R. And the R's we can ignore. So log A plus log Y is the same as log X plus log C. But they're logarithms, so we can add them up, and it turns into log AY is equal to log XC. And from there, we can conclude, just as we did before, and just as we skimmed over before here, AY is equal to CX. Now these two equations are very similar. It's A times something equals C times something. So let's give these equations names. 1, 2, and 3. Okay. So we could rearrange 2 and 3 to get something like z equals cy divided by a. Remember, a, b, c, x, y, and z, these are positive. A is positive, so we can definitely divide by it. We're not dividing by 0 here. Right? In fact, maybe a better way to write these is to highlight the fraction c over a. Okay. So we can have y in terms of x and z in terms of y, so that means we can get z in terms of x. C over ax, or c squared over a squared times x. So now we have y in terms of x and z in terms of x, along with some c's and some a's. Well, we've used these two equations. What about this third one over here? AB equals YZ. Well, we have Z in terms of ABCs and X, and we have Y in terms of the ABCs and X. So we could substitute both of these in to 1 and get an expression for X just in terms of A, B, and C. Once we have X in terms of A, B, and C, then we can get Y, and then we can get Z. So AB was Y, which is C over AX, Z, which is C squared over A squared X. And we could rearrange this. We can we get AB equals C cubed over A cubed X squared. A cubed over C cubed AB is X squared. And that means X is going to be A to the fourth B over C cubed, all raised to the power 1/2. I'd use the square root sign, but because of all the fractions, not the fractions, all the exponents, it makes more sense to take our square root as raising everything to the power of 1/2. Okay. So that's going to be A to the fourth, so 4 times 1/2, that's 2. B to the 1/2, and then C to the 3 over 2. So that gives us X. Okay. X, Y, and Z, well, that's just X. Well, what's Y? It's C over A times X. And Z, well, that's C squared over A squared times X. So C cubed over A cubed, X cubed. Well, we have X in terms of A, B, and C, so let's plug that in. We leave our C cubed over A cubed out in front. And then A squared, B to the 1/2 over C to the 3/2 cubed. So that's going to be C cubed, A to the 6, B to the 3/2 over A cubed. So those will cancel out. C to the 9 over 2. Okay. Fantastic. So the exponents in A are going to cancel out, and we're going to be left with a cubed on top. Nothing's happened to b. It's still b to the 3 halves. And then on the bottom, 9 over 2, that's 4.5. That's bigger than 3. So we're going to be left with c on the bottom. And 9 divided by 2, so 4.5 minus 3. It's going to be 1.5. So it's c to the 3 halves. So that's one way you could write it. Or you could write it as a to the 3, b to the 3 halves, c to the negative 3 halves. That's probably another acceptable way of writing it. I prefer this way because all of our exponents are going to be positive values. But there, we have x, y, and z in terms of a, b, and c, and that's exactly what we were asked for. X, y, and z in terms of a, b, c. So you might notice that once we overcame our fear of logs and actually used some of the properties of logs in conjunction with the information of the magic square we were told about, the question actually became very simple, and it was just a whole bunch of symbol manipulation. And that's something you'll probably find if you practice more contests. The weird function questions, the weird logarithm questions, they look scary. They are. I talk to students all the time. They are afraid of those questions because those functions have weird properties that they don't quite fully grasp, they're not accustomed to. But in actuality, those questions tend to be the easiest because they're usually just the most basic properties about logarithms quickly applied. And that tends to make the whole question very simple. So, if you are like the other students and you are scared of weird function questions and logarithm questions and exponent questions, do your best to seek those out. You can watch videos of me doing them. You can find solutions online. See how quickly the solutions are obtained. And hopefully then you will overcome sort of your anxiety towards logarithms. Because logarithm questions, I'm telling you, from someone who's been doing this a long time, they tend to actually work out pretty quickly, as long as you just apply the properties of logarithms. But that's question 6. That concludes part A on the 2011 paper. So in the next video, we're going to start B1, B2, and B3. Those are the written style questions. They're going to be a little longer, but hopefully they're a little more fun. And not that this hasn't been fun already. I just really like math contests. And hopefully you do too. And I'll see you next time.